Well, thank you very much, everybody. I feel a little as though we're preaching to the choir here. You guys know an awful lot about eye tracking, and I'm probably going to say a bunch of things that you guys already know, but I'm going to put it together in a way that sort of goes historically and builds up how eye tracking got to where it is today, because we stand on the shoulders of a lot of people who've done a lot of relevant research over the last 150 years. And it really, understanding what they went through makes it a lot easier to understand where the technology sits today. LC Technologies, it was basically founded on the hope and the expectation that eye tracking has a stunning future. And that assumption is based upon two fundamental tenets. The first is that the human eye is always looking at what's most important to us now. And if we're going to build devices out there in the world that want to help us, they need to know where we are looking, because they need to know what's important to us now, and they need to be able to respond to that. So if you had a teacher in broad areas of application or education and entertainment, there are a whole bunch of them. I don't want to get into a lot of the details there. But if a teacher, a reading teacher, knew what a kid was looking at as that kid was going through the text and knew where his gaze was, they'd give their eye teeth to know that information. An eye tracker will give them that information. And if we devise automated adaptive pedagogies that can teach based upon what the kid's doing now, it can be a lot more effective than it is without eye tracking. And similarly, if somebody's doing a VR game, if the system doesn't know where you're looking, how can it have a realistic interaction with your psyche at the time? So that fundamental premise that humans communicate eye to eye, we've got to give that same characteristic to machines, and then machines can be a lot more like humans. And that's the fundamental premise that LC Technologies was founded with 30 years ago. So there ought to be an eye tracker in every computer device, and that eye tracking available ought to be available to any application that's running on that device. So look into building eye trackers, the concept of what an eye tracker looks like. I'm going to review three things in this talk. First, we're going to talk about several of the key anatomical and physiological features of the eye, the beast that we want to measure. And second, we'll talk about some of what the early pioneers in the eye tracking industry have done, why they did it, and what they learned. And finally, we'll review a whole bunch of eye tracking performance metrics that we have to design to. So this picture you're all familiar with. It's a standard cross-section of the eye. You know all the parts, but there are two particular features that are important that I want to point out at this point. And one is the angle kappa. And the angle kappa is important because our eyes do not look in the direction. The foveal vision of our eyes is not perfectly aligned with the optic axis of our eye. And so when a measurement comes on our eye, we can see where the optic axis is pointed, but we don't know exactly where the foveola is on the back of the retina, so we have to make a correction to that. If we don't make that correction correctly, the accuracy of our eye tracker is out the window. The second feature that is important here is if you look very carefully at the corneal surface of the eye, it's not spherical. Most eye tracking software makes the assumption that it's fundamentally spherical, but there are a couple of things that don't follow that model. First off, there's a severe flattening of the corneal surfaces that it gets out towards the edges. So that means in the Pupil-Center Corneal-Reflection method, there's a nonlinearity that happens out there that needs to be accommodated in the software. And it's different for your eye than my eye. It's different between my right eye and left eye. And if we don't calibrate some of that information, it's not going to track me very well. And if we really want accurate eye tracking, we've got to calibrate people. It's a pain in the neck to calibrate people, but we have to do it if we want accurate eye tracking.
Can we take questions?
Sure.
What percentage of the cornea would you say would fit accurately to an ellipsoidal model?
It depends upon how sophisticated your ellipsoidal model is, because an ellipsoidal model can actually accommodate some of that smoothing. If you make an elongated ellipse, it actually starts to smooth out towards the edges, and that works. And another really nice thing about the ellipsoidal model is that you can put astigmatism into it. And so that accommodates several of the really key features of the variability of the human eye. So that's a wonderful thing to do, terrific thing to do. There's another feature of the eye that is extremely important, and it really allows eye tracking to happen in the first place. And remember that eye tracking, when we evolved our eyes, when nature evolved our eyes, there are two competing mechanisms going on. One is we want to have a very, very wide field of view. And the second thing is we need to have high resolution. You can't have both. And if you had both, if you had 180-degree field of view and all the resolution that we currently have in our central vision, our optic nerve would be about this big around, it'd be about 9 inches across. We'd have a half a cubic meter of brain function in the occipital lobe to handle all that stuff. It's not going to work. So nature found a really nice way to compromise on that. So it gave us relatively low res in the peripheral region with very, very high res, 70 times the intensity of cones at the center of the eye. And across the pupil, so this diagram is kind of neat because it shows these green cones up there show how densely packed the cones are. As a matter of fact, the cones are so densely packed in there that they are just the receptors, the cell bodies of the cones in the central foveolar part of the eye exist outside the central region of your retina. And all they do is send the wires with the receptors to those little green things. And then as you get further and further away from the center of the foveola, all the little purple dots in here represent the cones in your eye. And when you get way outside the region, then the cones are fairly dense and all you've got is rods. And rods and cones do different things. This next slide shows is a more scientific representation of what the rods and cones distribution in the eye is. So here's this really sharp spike at the central region. And the interesting thing is that when you go out to the peripheral vision, there's almost as much rod density as there is cone density. And this is the thing that people forget when they design displays, and particularly the concept of foveated rendering has to take into account. And that is, you can't make the assumption that just because you've got high cone density in the center and low cone density out elsewhere, that your eye sees blurry stuff out there. Yes, it is blurry. You can't make it out. If I hold my hand out here and wiggle my fingers, I know because of my own proprioceptive feedback that I'm pointing up or down, but you miss a lot of things. But the eye says, oh, there's a hand out there, but it doesn't necessarily figure out at that point. There's not enough information to figure out which direction your hand is pointing. Well, the fact that you can figure out your hand, if the hand were absolutely still, you couldn't make it out. But if it moves any, those rods are terrific at figuring out what's out there and moving in the environment, because It wants to figure out that there's this leopard out there that's about stalking you, and you need to find that thing, and you need to make out what it is. So if it's moving, you see it, and then you swing around, your eyes swing around and look at the thing. So this then brings us to the next stage of what's going on. If we have this nice central vision with high resolution and low cone resolution out in the periphery, that means that the eye has to move. It can only look one place at a time. If it wants high resolution and I want to look at your right eye, I can do that, but I can't see your eyes very well. I can barely make out a face over there. So that means that we have to have, that we developed, that nature went to all the trouble to develop this concept of fixations and saccades. We fixate our eyes right on one place. Those muscles that we have that you see up here, the ocular muscles, hold my eye extremely still for those 250 milliseconds that it takes to get enough photons to get a good image of that foveal area, and I can make out and get the detail that I want. And then snap, those same muscles, snap your eye over to the next place and take a picture someplace else. This happens roughly 4 times a second. At a 4 hertz rate, our eyes are darting around and they hold extremely still, they snap extremely fast, saccade to the next place, and they fixate again. So that behavior resulted from the design of the eye to balance this wide field of view versus a high resolution trade-off. So the output of the eyes goes back fundamentally to the occipital lobe, the visual cortex in the back of your brain, where it does all its magic and figures out what's out there, and gives us all the feedback that we need to interact with things. But for eye tracking, there's another really important element of the brain, and that's the superior colliculus. The superior colliculus is, Pete, would you get me my pointer out of the back of my briefcase there? The superior colliculus is that part of the brain that, in one sense, adjudicates, figures out for the whole brain where the eye is going to go in its next fixation. So the SC is, thank you. So the SC sits right there, right in the center of your brain. So the SC gets data from all over your brain, and all your different brain functions want some visual input. Everybody's starved for visual input. Well, who wins? Your eye can only look one place at a time. It's a winner-take-all strategy, and the SC is the one that makes the final resolution of that and tells your eye where you're going to go. So if you're reading a book, the next thing you want to do is move your gaze to the next chunk of text. If the baby screams off there in the right someplace, you say, oh, that part of your brain wants to go pay attention to the baby. And then if you happen to be walking down the street at the same time you're reading the book, this is a silly example, but it demonstrates the point, and you trip over something, your vestibular system says you better look at the ground because you're going to be breaking a fall. So it's got these 3 inputs all at the same time, and it's got to decide which one to do. Keep in the back of your mind, while it's making this decision, it's making the decision, what's the most important thing for you to look at right now? Because it's that fundamental process of the brain and the fact that we have a central vision that enables eye tracking. That's the fundamental reason that we can do it, is because that information, nature poked a hole in our skin to let the photons into our brain that allows all of this to happen, and we've got to take advantage of that to build machines that have the same kind of eye contact that we humans do. So the SC is a really kind of neat democratic thing. What it's able to do is get these inputs from all over the brain. And if you unfold the thing, it's like a map. And you can see areas poke up. If your eye is pointed right over there and your peripheral vision sees something, it says, oh, I want a saccade of that many degrees to go over and look at you instead. If you happen to be waving your arms at me, you're not, but that's what it would do. And something else, the vestibular system says, something's happening over there. I want a saccade to go over there. It's got this map and it's building up these potentials of all these important areas. And it's being very clever about it because each part of the brain says, I want visual attention, but I want it with a level 6. Your vestibular system comes back and says, I want it, but I'm a 9. So that spike grows faster on the surface of the superior colliculus, this map of your retina. And finally, one of these spikes pokes through a threshold and bam, the superior colliculus fires off, and that's where the eye goes. And that's where the next fixation is. So the key point here is that an eye tracker can't see what all the alternative options were when you made the decision to go. If we can figure out that problem, that'd be pretty cool. But one thing we can see is the final decision that it did make. And that decision is the most important thing to your brain at that point in time. So the role of the SC in eye tracking is a really big fundamental element of what allows us to achieve these goals of getting systems that make eye contact with you. So what happened? How do these guys build this equipment in the first place? What's going on? Well, sure. Sure.
What are the two colors? Purple and
Oh, these are the visual pathways. The purple is from the left eye, and notice, so it goes through the optic nerve, the optic chiasm, the optic tract, back here to the pulmonar region. Some signals go back up into your superior colliculus, others head back into your visual cortex, and then from the visual cortex, they go up to the frontal lobe, and from your frontal lobe, that's where a lot of the decisions are made that feed back down to the visual cortex. They all cross over. For some reason, your right eye is connected to the left half of your brain and vice versa. And one thing I don't quite understand, and that's a fabulous question, is what happens in the central region, in the foveola of your brain. Where is it connected? Is it divided down the middle? I don't know. Doug Munoz at Queen's University did a lot of the research on that and found out the connectivity of all this sort of stuff. He did it with monkeys. They were nasty experiments, but he found out an awful lot of the stuff. And that's where it was verified that these crossover things happen. It was speculated before that because somebody'd have a right brain problem or a damaged right brain and their right eye wouldn't work. And everybody thought, well, that's interesting. But it wasn't until Munoz did his work that we actually proved that that was the case. So early people in the researching in eye tracking wanted to find out, how's the brain doing this? What's it doing? And so this guy, Delabarre, back in 1989, built a device. This is not Delabarre's device, by the way, but he built a system. He took a needle and he stuck it in the eye. He took a little piece of plastic and plaster and glued it to the eye, and this wire sticking out, this needle sticking out with a string coming off of it, and the string dragged along something on a strip chart recorder, and he recorded all these eye motions, and you could see from the strip chart recorder, there it was, fixation, saccade, fixation, saccade, fixation, saccade. So he demonstrated all that with that crazy equipment 170, 80 years ago. So eye tracking's not new. It's been around for a long time. And then this guy Shackel, and there's several other people in this history, but Shackel then came along and he figured out that there's this potential across the eyes. If you put a pair of electrodes on right and left side of your eye, there's a potential across there. And as your eye rotates from side to side, it presents a variable resistivity that can be measured in the measured voltage across the eye. Well, that was a hell of a lot easier than sticking a needle in your eye, attaching a needle to the corneal surface of your eye. So EOG came around, and that was really cool technology at the time. And then Yarbus. I'm sure all of you guys know Yarbus. But the keen thing that Yarbus did, he actually built some neat eye tracking equipment. And pass this around. This is his device. So this device, somebody put their head in the headrest here, and these two cameras looked at their eyes, and they recorded the data with video. So video eye tracking finally came on the scene. And these guys, he was doing his work in the 50s and the 60s, 1950 and 60s. So this is, even that work now is 70 years old. And he was able to collect the device. Those video cameras recorded all the data, and then by hand, frame by frame, they'd go through and calculate the corneal reflection and the pupil-center, calculate that data. They'd infer a calibration for that person's eyes and map out the gaze trace. It was beautiful research. And what he found was, well, his chief purpose was not to build an instrument. He did that, and he built a wonderful instrument. But the key thing that he found out was what people do in visual search. And they do exactly what you'd expect them to do, but he documented. What you'd expect them to do is when somebody walks into a room, you'd expect them to take a general look all over, pick up the big picture, something will attract their interest, and then they'll start zeroing in on some particular detail. And he documented that that's what happened. So that was really another fundamental piece that was putting together this whole picture of how the eye behaves. So then there were these three guys, Merchant and Mason, well, two guys really. It was Merchant and Morrissette. These guys were working for Honeywell, and Honeywell had a contract. They had this idea that they took out to Wright-Patterson Air Force Base that they wanted to actually control something with their eyes, not just see what they did, but use their eyes as a control device. So what they did was come up with this idea of, well, the basic application was they wanted to do targeting. So pilot was flying a plane, he'd look over at something, he'd say that's what he'd say that's what he wanted to do, and he would indicate to a target acquisition device by pressing the button once. If the target acquisition device actually picked it up, you'd push the button again, and the missile would go off and kill the target. Really cool idea. But they had to do this. Now they have got to get eye tracking working in real time. But they did it. So they got a camera that could capture the image in real time and digitize it. They took all the algorithms for computing the pupil-center and projecting the gaze, and they put that stuff into computer programs, and they got gaze point calculation, programmed up gaze point algorithms. And when this thing worked, it generated eye tracking data automatically and in real time. These guys were the Wright, in my opinion, these guys were the Wright brothers equivalent of eye tracking to flight. The Wright, Orville and Wilbur got lift, power, and control all solved simultaneously to get this plane off the ground, fly 120 feet stably and land. And these guys, Merchant and Morrissette, built the first eye tracker that was automatic, real time, and pretty bloody good accuracy. They use the pupil-center corneal reflection method, which is a standard today. So back in 1969, these guys published their results 50 years ago, and we're still using that concept today. So these guys laid down a tremendous foundation for how eye tracking would work. they use the bright Pupil-Center method as well. And LC Technologies does that today. A lot of other companies have abandoned that because to get coaxial lighting is very, very difficult to implement that in hardware in a small piece of hardware. But it gives you the very good image processing results because it gets very good contrast between the pupil and iris. And so you can get an accurate pupil center measurement much better with a bright pupil effect than you can with a dark pupil effect. So what happened in the Morrissette version and Morrissette work? Well, there were three big problems with this device. First off, they implemented the image processing algorithms in a PDP-11 computer that sat in the corner of the room. They were never going to get that in a fighter plane. Number two, the room had to be dark. That wasn't the environment that you were in, that a pilot would be with a canopy over his head and the sun shining in. No way that was going to work. So, let's see, there was a third problem. Oh yeah, and it didn't allow any head motion. You had to hold your head pretty still. You're looking at a Yarbus device. It was the same type of deal. To get a high enough resolution image of the eye, they had to use a really high telephoto lens that only had a very narrow field of view. You couldn't move your eyes very much, or your head very much, and have the eye tracker continue to see you. So that project just basically died, and eye tracking sort of went underground for about 20 years. But one thing really did come out of those guys' work, and that is a list of eye tracker performance metrics. And this is a hodgepodge list. I mean, the list goes on and on and on. It gets boring, and I'm sure you guys are fairly familiar with it. But eye detection accuracy. The image processing not only has to be able to measure the corneal reflection in the pupil center, but if it doesn't recognize, detect the thing that's an eye in the first place, if it detects the corner of my glasses, it can measure what it thinks is the pupil center and corneal reflection perfectly, and you're going to get garbage data. So you have to have a good detection algorithm that differentiates between eye and non-eye objects. Then you have to, the gaze prediction accuracy, you have to be able to measure those things precisely. And then you have to have some kind of freedom of head movement. And then you have to have the ability to accommodate a whole bunch of different eye variability. Then glasses and contacts, tolerance to ambient infrared light, ease of calibration, safety. There's certain maximal permissible exposures that you can put on the eye, and it's got to work fast enough. It's got to work really fast in certain applications. And then size, weight, power, and cost, all of those things. There's a massive list of things that you have to do. So there are a lot of problems in the industry, and that's just a summary of them. So I want to just give a few examples of images that have some of these problems that are difficult to process. Reflections cause a lot of clutter in the images. This is an example of a person sitting in a room with a remote eye tracker. They happen to have glasses on, but you can see this window in the background reflecting off the glasses, making a mess of that eye image. Most image processing algorithms look at that thing, they throw up their hands and they say, I don't see an eye in there. You and I can see it, so we know the information's embedded in there, but we haven't yet developed enough really smart algorithms to dig that information out of that cluttered image. And then over here is an example of reflection of the LED, the eye tracker's own illuminator. Well, you can't see it here, but there's a big reflection off the glasses itself, and there's some internal reflections up here, and you can't tell which of those is the real corneal reflection. There are a bunch of glints there, but how does the image processing know how to dig out the right corneal reflection, or the right glint as the corneal reflection? Here's a case where glasses the reflection off the glasses are getting right close to the image of the eye, covering up the corneal reflection completely. That's not going to give you any data. Over here on the left, we have contact lenses. Contact lenses have these little things stamped in the middle of them that you and I can't see, but since eye trackers work in the infrared region, they reflect off this thing and they come back with this little symbol. You figure out who made the damn contact lens. That's of zero interest to eye trackers, but they can get confused by that data in an image, and we got to design algorithms that just say, I got it. Ignore that data and proceed on with calculating the eye image. Hardline bifocals. The camera's looking at your eye from coming up, looking from below, and it typically sees your eye right through that cut in the glasses. So the top half of the pupil seems to be one thing. You see it through the top lens and the bottom half through the bottom lens. Where's the center of that pupil? We got to design algorithms that handle that stuff. Oh, the contrast on this is fairly poor, but the real corneal reflection is sitting right there. And that corneal reflection straddles the perimeter between the pupil and the iris. So if we include this thing in the pupil, are we going to compute its pupil center right? It's sitting right on the gradient. The corneal reflection is sitting right on the gradient between the pupil and the iris. It's coming off. Where's the center of the real center of the corneal reflection? Image processing has got to handle that problem. Another big problem in eye tracking is measuring the range to the eye. It's extremely important that we know the distance between the lens and the corneal surface of the eye. Not just someplace out in the center of the eyeball, but right to the corneal surface of the eye. Because the glint pupil vector, so here's a standard glint pupil vector when somebody's sitting in a nominal location looking at a point on the screen. And then as the eye were to move backwards, there's a double-barreled effect of making an error in range. The first is if the eye were to move back and you didn't know it, you being the eye tracking instrument didn't know it, the whole glint pupil vector would get smaller first because the eye is just further away. And the whole image got smaller. The second thing is that as your eye moved backwards, if it's still looking at the same gaze point, it literally started to point downward. So its orientation was different. But if we didn't know those two things were happening, we would project a very different gaze point. We'd project somebody looking way down low on the screen. So we have to measure gaze accurately. That's one of the things that LC technology spent a lot of time on, was being able to measure that. We use what we call the triangular or the asymmetric aperture method. And it's based upon the fact that the corneal reflection looks like a point source of light out in space. And it's located right behind the corneal surface itself. 1/2 the radius behind it, but that's where it is. If the camera lens is in the right place, all these rays coming from that corneal reflection back through the lens and to the sensor surface on the camera will converge in a perfect location. But if, for some reason, the eye moved forward or back, or conversely on the sensor plane, the camera, the lengths were too long or too short, the lines from that point wouldn't converge on either side. But there's a really cool property, and that is if we make a triangular aperture whose shape is different upside down than right side up, we can look at that corneal reflection, and it'll be blurred on either side, but we can tell whether that thing is right side up or upside down because of a triangular aperture. So if we can design a control loop that drives this thing back into focus, we're good. We've got it. We can measure that. And we can use the Gaussian lens equation to calculate exactly how far the camera is focused. And so we can make very, very precise measurements down to 1/10 of an inch. And that 1/10 of an inch is extremely important for getting accurate gaze point calculations. Nope, I'm going the wrong direction here, sorry. Large and small pupils. This is a problem with the Pupil-Center method or with the bright pupil method, because big pupils typically let a lot more light into the pupil, let a lot more light back out, and so they end up being very bright. And tiny little small pupils tend to just get very, very dim. And we have to design image processing algorithms that can handle that wide dynamic range of pupil amplitudes.
Are these examples using the triangular aperture?
Yes. And you can see it back there in the demo after the fact. You'll see all that stuff. We've got it demonstrated so you can actually see the mechanism of how that works. This is a particularly cool example because there's a tear glint down here. Light from the LED is going and reflecting off a tear glint in the bottom. There's a tear glint at the top. There's a tear glint down there at the inner canthus. And there's a real corneal reflection, and there's another reflection that comes from an internal thing on the lens. How do you find the right corneal reflection? Which one's the real one? If your image processing doesn't handle that, you're going to produce bogus data. Eyelashes come down. This is not good contrast here. You can see it beautifully on my machine, but you can't see it up here very well. But there are eyelashes coming in. How do you map the perimeter of that pupil? Does that clutter screw you up? If it does, your eye tracker isn't going to work very well. We got dry and congealed corneas. LC Technologies works with people with disabilities. And so we see all the corner cases. And a lot of people with ALS, for example, have lost their blink reflex. Not only can't they speak and they can't use their hands, their eyes, the ocular muscles still work because they're connected directly to the brain rather than going down through the brain stem where all that, there's loss of connection between the brain and the parts of the body that the brain wants to control. So your ocular muscles work, but your blink muscles don't. Your eyelid muscles don't. They are connected back down through the brain stem. So the data you get there, if somebody doesn't blink, you get congealed tears all over the front of your cornea. You gotta, it'd be nice to handle that. In this case, you have dry eyes, so you don't blink enough, so the corneal surface doesn't get lubricated properly. There's no corneal reflection there. There's a nice tear glint, but there's no corneal reflection. What does your image processing do with that? If your eye's in motion, you get a very blurred image of the eye. So you have to take high-speed photography to get images that are still enough that you can interpret correctly. One of the serious problems in eye tracking is squinting. If you squint, you lose the corneal reflection. If you don't have both the corneal reflection and a pupil center, the PCCR method doesn't give you the answer you need. So you need to start putting other illuminators around at different places that when you're squinting, it'll continue to work. Why is squinting a problem? Mostly because when people are playing a game and they start to get intense about something, the first reaction you have is to squint. You just want to say, what in the world is going on there? And you squint to look at it. And if you're depending upon that eye tracker to track you while you're doing that and you squint, you're in trouble. So we need to tackle that problem too. LC Technologies has taken a good step toward that. We did it for people with disabilities because they squint for a different reason. They've got ptosis of the eyelid, or what we call droopy eyelids. Their eyelid control, as we said before, isn't working perfectly, so the eyelids start to come down and they impinge, particularly on large pupils like this one. So our image processing algorithm looks at that pupil and it says, oh, the eyelid actually is occluding the top edge of that thing. And so when it fits the pupil, it doesn't just find the center of mass of that thing. It finds legitimate, apparent pupil perimeter and fits only to that data. There's a little secret in eye tracking, or concept in eye tracking that's not very well understood, and that is the pupil center does not open and close precisely about a given point. You've got a sphincter muscle that's trying to constrict your pupil and radial muscles that open it up. And when your pupil opens and closes, it doesn't go around some nice constant point there. The smaller pupil may drift over here, a large pupil drift there. And if it starts to drift around, the pupil center corneal reflection method doesn't know that the pupil center shifted. And so it's using the old calibration, assuming a calibration of the pupil center of the diameter when the calibration was taken, and then it starts to drift. A lot of eye trackers had that problem. So we try to solve that problem too. Calibration, you have to have a calibration if you want accurate eye tracking. That's really all I'm going to say there. There's a LC Technologies has built this thing that we call an Eyefollower. And there's a fundamental trade-off in eye tracking between accuracy and tolerance to head motion. If you want a nice tolerance to head motion, the typical solution in the industry is to widen out the camera field of view. Good, we can see you wherever you are. We can get your eyes, we can track them. But how good and how well can you measure the pupil center corneal, the glint pupil vector? As the resolution goes down, you can't. And there's this crazy trade-off of our eye trackers now have a very narrow field of view, but you need a wide field of view. So camera technology will get you a factor of 2, maybe 4 in dynamic in field of view, but we want 10, 15 times the field of view. That's not available in camera technology. We can't get that high resolution. So we basically borrowed a model from our own human eye, and that is we have a robotic device where the eye tracking camera is actually on a gimbal that moves around as your head moves around. And we have another camera, a wide field of camera that says, oh, that's where the head is. So if the eye tracking cameras are pointing off here someplace and your head's over here, the wide field of view camera, just like our peripheral vision, will say, oh, there's the head, go look there, and boom, our system will saccade over and fixate on your eyes and start tracking your eyes. So we get always a very high resolution image of the eye, no matter where your head is. And at the same time, we can track your head over a large range. So we've got our own little robotic system to do that, and you'll see a demo of that in the back. You don't need that for all applications. If you're doing VR glasses, that's not a problem, but for remote eye tracking, it's a very good solution. So where does the technology stand today? Well, there are a lot of pretty simple, quote, good enough solutions. The systems that are out there now, they track a fair number of people, and they track a fair amount of the time, but they don't get everybody all the time with high accuracy. So the industry's got a long way to go to make that thing work to be really robust across the entire population. We need to make them yet smaller and cheaper. Today, there's these little bars coming out. Cool, you made it smaller, but you gave up all that accuracy. You gave up the robustness and tracking. That's not a good enough trade-off today. We've got to do better than that. So we've got to have all kinds of fanciness. As I was going through all those images showing about how you process different kinds of images, problem images to be able to cover a broader range of the population. And accuracy really remains a key problem. So the next steps, there are obviously 2 different categories of product design. There are remote head trackers and head-mounted eye trackers. So we have to design both of those for different applications. Hardware miniaturization is really a key. It's a tremendously important thing. We've got to build much smaller cameras. We got to build cameras that are adapted to the specific purpose of eye tracking, not taking off-the-shelf cameras and just throwing them in there and making them work. Same for the lenses. There's more glass and stuff in those off-the-shelf lenses than we ever need in eye tracking. We need to throw most of that out, but there are certain characteristics that don't exist in the lenses that we want that should be built into eye tracking lenses. That optimization has really never been addressed adequately in the rest of the industry. But the key thing is, I was mentioning before, we still need to do this image processing. We've come a long way in that area, but there's a lot more work. That is the tougher problem of all of these things. The hardware is really pretty straightforward. You get a bunch of good engineers in a room and they'll make it smaller. We can solve those problems. But the thing that handles the diversity of the human factor in our eyes lies in the software. And so we have to do that. And I believe that LC Technologies has delved into that problem better than anybody else in the industry. Well, thank you very much, you guys. It's been a fun talk and good questions.